Hi everyone. Just addressing your feedback from today, our lecture on predicting acid strength. So I had a question. So to determine acid strength, do we just figure out which molecule has a more polar OH bond? It seemed like all the examples that we did today all involved OH bonds and just figuring how much how polar it was. And yes, very frequently that is what you're going to end up doing, is just figuring out which of them is going to have a more polar bond, but it's not always quite that simple. There is always going to be exceptions. It's never a neat thing. There's frequently a bunch of different factors to consider, like case in point, H2O versus H2S. H2S is actually a stronger acid because it does a better job of accepting these protons. Even though it's less electronegative than oxygen is, it has a higher electron affinity because it's a larger atom and it can accommodate those extra electrons a little bit more when it forms HS minus. So it's a matter of how well an atom can accept electrons, and that is very frequently related to electronegativity and bond polarity, but not always. But at this level, yeah, you can generally say the more polar the bond, the more likely it is to accept electrons and therefore donate a proton. Along those lines, could you give us a quick reminder of how to draw Lewis structures? So what I would say to that is there's no way I can give a thorough explanation of how to draw Lewis structures in a feedback video, so I would say check sections 9.6, 9.6 through 9.9 in your textbook. They go through how to construct Lewis structures for most molecules. But the general rule of thumb here, the general strategy is to, 1, count the number of valence electrons, construct a basic skeletal structure, fill up octets, make sure everything has an octet, and then if you have the wrong number of electrons, if filling up the octets made it so that you didn't have the correct number of electrons, then use double and triple bonds of electrons. So case in point, I'll do a really simple one. Well, I kind of already did it right here for H2S, but H2S, the total number of valence electrons, sulfur normally has 6 valence electrons, each of the hydrogens has 1, but I have 2 of them, so I have 8 valence electrons. I'll draw a basic structure here where I have the sulfur in the middle, so it's going to be bound to these 2 hydrogens. And then so that gives me my basic structure. Then I fill up my octets. So I've got 1, 2, 3, 4, 5, 6, 7, 8. An octet for the sulfur. Hydrogens violate the octet rule. They only have a doublet. So that's good. And then I check to make sure that I have the right number of electrons present. And if I don't, then I would need to make double or triple bonds. But here I've got 1, 2, 3, 4, 5, 6, 7, 8. And I was only supposed to have 8 valence electrons total in my Lewis structure, so that one is good. I had a question here which I admit I was a little confused by. So fluorine is extremely electronegative, but it's harder to break the HF bond than, HF bond. So I believe you're referring to my first set of examples where I was looking at a comparison between HF and HCl. And this is a confusing example because even though fluorine is more electronegative than chlorine, fluorine actually has a larger dipole. This molecule ends up being a stronger acid than HF. Again, there's a couple reasons. One is just that the bond itself is stronger, so it doesn't break as easily. The other reason here is that chlorine has a higher electron affinity than fluorine. Even though fluorine has a higher electronegativity, meaning it tends to pull electrons towards itself in a chemical bond, chlorine actually has a higher electron affinity. Its ability to completely gain an electron and the amount of energy it releases when it gains that electron is actually higher for fluorine. And as a result, the chloride ion is actually more stable than the fluoride ion. And that means that the HCl molecule is more likely to separate and form a chloride ion than the HF molecule is likely to separate and form a fluoride ion. Then I admit I was a little confused by your next question, your follow-up question, which is oxygen is more electronegative than chlorine, yet oxygen is more favorable. Why? So I'm not entirely sure what you mean by more favorable. So if you'd like a further discussion on that, please could you please expand upon that question? Either come to me in my office or shoot me an email and I'll try to answer that question. I'm still having trouble determining the strong acids. So today's lecture was not about how to identify the strong acids. Today's lecture was about how do you predict relative acid strength, whether one molecule is stronger than another one. That's mostly what we were focusing on today. Today's lecture is not really going to give you the ability to determine which acids we would classify as strong acids, meaning they completely dissociate, that their Kas are so large that we just say they go to completion. For that, I would say if you just want to be able to determine which acids are categorically strong acids, I would say just memorize them. The strong acids are going to be HCl, HBr, HI, nitric acid, HNO3, sulfuric acid, H2SO4, and perchloric acid, HClO4. Those 6 are what we would consider strong acids. Some of them are stronger than others, but they are all classified as strong acids. Today's lecture was just trying to figure out, okay, relative to each other, two molecules relative to each other, which one is stronger? And then on that, you make the basis. It's better to make it on the basis of Lewis theory, how well something is at accommodating extra electrons or electron pairs. Along the argument of Lewis acid-base theory, I had a clarifying question here, which was looking at one of the examples I gave, which is between NH3 and boron trifluoride, and they make NH3BF3. Your question was, is this one the acid and is this one the base? Yes, the ammonia here is a base. It has a lone pair that it donates to the boron and makes a bond between the nitrogen and the boron atoms. And so we would say that that method of action, electron donation, the fact that the ammonia is the one that's donating them, that's what makes ammonia a base, according to the Lewis classification of acids and bases. I don't understand how to predict electronegativities. For predicting electronegativities, that's going to be an application of your knowledge of periodic trends. So the general trend in the periodic table is that electronegativity increases across a row and it decreases down a column, whereas I normally remember it as increasing up the column. So the most electronegative species is the fluorine molecule, or fluorine molecule, the fluorine atom. Fluorine is the most electronegative element because it's all the way in the top right corner of the periodic table. And again, if you would like a background, you'd like a further explanation about how do you predict relative electronegativities, see section 9.5 out of your textbook. Or again, shoot me an email. Alright, so that was all the questions from today's lecture. I had 2 questions from Wednesday's lecture on polyprotic acids, which I didn't create a separate video for, so I was just going to do that here. I had one question: why is it harder to remove the second proton from a polyprotic acid? So let me try to illustrate that here. So if I have an acid, say H2S, and it's acting as an acid, it donates a proton to water. Or, you know what, not even going to worry about the water. I'm just going to show this bond breaking here to say that it's going into H plus and HS minus. And then when it donates its second proton, it goes from HF minus to H plus and S2 minus. And your question is, why is it that it's harder to remove the second proton than it is to remove the first proton? And that you can explain in terms of electrostatics. Coulomb's law, opposite charges are attracted to each other. So in the first case, I have a single charge, a single positive charge, and a single negative charge. They should be attracted to each other. So when I'm trying to separate this molecule, I'm trying to separate a positive charge and a negative charge. Coulomb's law tells you that the Coulomb force, the attractive force between two charges, is proportional to the magnitude of those two charges. The larger the charges, the stronger the attraction. When I try removing the proton from the second proton, I'm now trying to separate a singly positively charged ion and a doubly charged ion. And those two are going to have a much stronger Coulombic attraction to each other, which makes them harder to separate and therefore harder to take off the proton from the molecule. So that's the basic explanation of why it's always harder to remove a second proton from the molecule, is that their species now already has a negative charge. Previously it was neutral, and I'm trying to pull away a positive charge from a neutral molecule. Then when I try taking away the second one, the molecule is already negatively charged, and that proton is inherently attracted to that negative charge. Let's see here. And then I had somebody ask, could you please explain how to calculate hydronium concentrations, how to calculate the pH of a polyprotic acid? Sure, I will show you how to do that really quickly. I'll use H2S, hydrosulfuric acid, again as my example here. So let's imagine you have a 1 molar solution of hydrosulfuric acid, and I will tell you that the Ka, the first Ka1 for hydrosulfuric acid is about 1 times 10 to the negative 9, and Ka2 is about 10 to the negative 19. So again, it's about 10,000, sorry, not 10,000, 10 to the negative 10, what is that, 10 billion times weaker to remove the second proton. So they come off in stages. I just showed you that. 1 proton comes off at a time. So for the first proton, you have this reaction, H2S. It donates it to water and produces hydronium and the HS minus ion. So I would do this with an icebox because, again, it's an equilibrium process and there's an equilibrium constant associated with it. I know that the equilibrium constant Ka1 should be hydronium concentration times HS minus over concentration of HS2, or rather H2S. So I know if I start with 1 molar, and then I assume I'm starting with no hydronium and no HS minus, so I lose a little bit. the reaction goes forward and I lose a little bit of H2S and I generate a little bit of hydronium and a little bit of HS minus. So my equilibrium concentrations are 1 minus X, X, and X. And if I plug those values in here to my expression for the law of mass action, I get X squared over 1 minus X. Now, Ka1 is quite small. It's 10 to the negative 9. So I don't expect this reaction to go to completion, and I expect X to be quite small. So 1 minus something small is still about equal to 1. So I have this should be approximately equal to X squared over 1. So I can then solve this equation quite easily for X. So I can move over the 1 and take the square root, and I get that X, which is my hydronium concentration, and also my HS minus concentration, is going to be the square root of Ka1 times 1. So again, I multiply over the 1, and then I take the square root of it. That ends up being, I calculated this, 3 times 10 to the negative 5. All right, so that's my hydronium concentration and my HS minus concentration. And then the idea is, okay, that's just to get off the first proton. So let me put a little demarcation here. That's just for the first proton and the first equilibrium reaction. The second equilibrium reaction is the fact that HS minus can also donate protons to water. So that's going to get me some hydronium and some S2 minus, and then I will do another icebox here because this is an equilibrium process, except my icebox is going to be a little bit different. My HS minus concentration, that's dependent upon however much HS minus I made in this first equilibrium reaction. So that should be 3 times 10 to the negative 5. Water we don't care about. Hydronium concentration is also 3 times 10 to the negative 5. We know that the first reaction produced some hydronium, and we already calculated how much there was. Now there's already some hydronium in solution, more so than what you would get just from the autoionization of water. So it's a non-negligible amount of hydronium now present. And we can assume that there is no S2 minus yet produced because we assume it hasn't dissociated yet. So at that point, you can say, okay, I'm missing one of my products, so the reaction should shift forward and produce some of that product. So I will lose reactants, generate a little bit more hydronium, and generate some S2 minus. So my equilibrium concentrations now are 3 times 10 to the negative 5 minus X, 3 times 10 to the negative 5 plus X, and X. And if I plug these equilibrium concentrations into the law of mass action, now my law of mass action looks like this. So this will be Ka2 is equal to concentration of hydronium times concentration of S2 minus divided by concentration of HS minus. That should be 3 times 10 to the negative 5 plus X times X divided by 3 times 10 to the negative 5 minus X. All of that is equal to Ka2, which is 10 to the negative 19. Now, at this point, you could completely solve this algebraic equation, solve for X yet again. Once you solve for X, you recognize that the concentration of hydronium is 3 times 10 to the negative 5 plus X. So again, you can solve this equation, this algebraic equation exactly. It's a quadratic expression, so you can solve for it using the quadratic formula. If you multiply everything out and move everything over. But yet again, we can make a numeric approximation here. If Ka2 is only 10 to the negative 19, this reaction is not going to go very far to completion. X we yet again expect to be quite small, significantly smaller than 3 times 10 to the negative 5. So both of these terms, where I'm adding on X and where I'm subtracting off X, those both get, we can ignore those, so I get 3 times 10 to the negative 5 times X divided by 3 times 10 to the negative 5 is equal to 10 to the negative 19. These guys are going to divide out, and I get that x is about 10 to the negative 19. So point being here, I think I showed this graphic, I showed this with a picture, is that doubly deprotonated one, we don't expect there to be many of those. That first proton, this is a weak acid, that first proton doesn't come off very easily, so I don't produce much of the singly deprotonated species. And then not only is that singly deprotonated species low in concentration, it's even less likely to donate its proton than the first one was. So you don't produce much S2 minus, and as a result, you also don't produce a heck of a lot more hydronium. So your hydronium concentration here should be, so we said that X was 10 to the negative 19. Your hydronium concentration should be 3 times 10 to the negative 5 plus 10 to the negative 19, which is around 3 times 10 to the negative 5. Which is the same as what I predicted from the loss of the first proton. So what do we learn here is that generally speaking, for most polyprotic acids, the hydronium concentration is essentially determined by the first proton donation. Subsequent protons being donated come off at such a low rate because the equilibrium constant is so small that you can essentially neglect them. And you can usually get away with just figuring out the hydronium concentration from the loss of the first proton. There's really only one exception, or maybe not one exception, but there's only a couple of small exceptions to that I can think of, where, again, you would do the same analysis. You would do the exact same analysis, except that you might not be able to make these approximations. That's the only difference. So the only examples I can think of for that would be something like sulfuric acid, where the first one is very large. For sulfuric acid, H2SO4, Ka1 is much, much larger than 1. It basically behaves as a strong acid. And then Ka2 is about 10 to the negative 2. So it's not negligible compared to the concentration of sulfuric acid. And I think carbonic acid is also an exception there. But again, I usually will not be asking people to do calculations for exceptions, and I probably am not even planning on giving people calculations based on polyprotic acids, because as I just mentioned, it basically just behaves mostly like a singly protic acid in terms of predicting pH. So I hope that was instructive. If you have additional questions, again, I will be available throughout the entire break to answer questions via email. Hopefully, please feel free to contact me, and I will see everybody after the break. Have a fantastic spring break.